Hello and welcome everybody to today's Saturday morning lecture, which is the second of 4 events this fall. My name is Stanley Yen, and I will moderate today's session. If you've ever attended one of these events in person at TRIUMF, I'm the one who's been introducing these for the past 16 years. And during my time as a neutrino researcher and as a lecturer at UBC, I've been gratified to watch a whole generation of students and the general public pass through TRIUMF to attend these lectures. This year, because of COVID, our lectures have gone online. Today, I welcome everybody to hear about how physicists combat COVID-19. In part 1 of this talk, Reiner Kruecken, TRIUMF's Deputy Director of Research, will tell us about the MVM ventilator project. We will then have a 10-minute question and answer period. In part 2, Dean Karlen, Professor of Physics at the University of Victoria, who also has a joint appointment at TRIUMF, will explain how his data science expertise has been employed to model the spread of COVID-19 and inform government policy. This will be again followed by a 10-minute question and answer period. Your questions for the speakers may be submitted via the chat box on the live stream. In the live stream description, you'll also find links to learn more about our speakers' careers and accomplishments. So our first speaker is Dr. Reiner Kruecken, Deputy Director of Research at TRIUMF. Welcome, Reiner.
Thank you, Stan. It's great to be here this morning. Let me start sharing my slides. So it's a great pleasure to join you all this morning to tell you about an exciting story. A story of how an international collaboration of physicists developed this low-cost ventilator for COVID patients and did so in record time. And the ventilator you can see here is the so-called mechanical ventilator Milano. So let me tell you that story. If we look back at the early days of the pandemic, you see here the patient new cases count and traces in Italy and Canada. And our story really begins in March 19th, in the really still in the exponential phase of COVID patient growth in Italy. Italy was one of the hardest hit countries in the world during the early phases of the pandemic, with thousands of COVID cases per day. While many only have mild symptoms, we do know today that up to 5% of people contracting COVID will develop critical illness requiring intensive care treatment. Of those critically ill, many will require mechanical ventilation. So these critically ill COVID patients are usually put into an induced coma and are intubated with the ventilator, then providing breath with a certain rate, a certain preset rate, certain pressure or volume of air going into the patient, and allowing the patient to exhale, to the air to flow back out through a second line of the so-called breathing circuit. The ventilator itself monitors the parameter like pressure, flow of air, the volume, the rate, and so on. In northern Italy, the situation was particularly dire in March. The hospitals were overwhelmed with COVID patients and hundreds of people died each day. And the country was running out of ICU beds and out of ventilators, and they weren't able to produce any in the country itself and couldn't purchase any from other countries either. It was at that time that Princeton professor and dark matter physicist Cristiano Galbiati, who you see in the Zoom window on the left, was stuck with his family in his hometown of Milan. Seeing this crisis and knowing how some of the doctors in the COVID wards, he decided that something needed to be done and he could do it. He conceived with some colleagues the concept of a new ventilator that could be quickly produced, ideally in Italy, and possibly then help in this crisis. He secured the help of a local company, an electronics company called Elemaster, where he set up the headquarters of the VM efforts. And just doing that was a big effort because the local government had to allow them to come out of the lockdown and open the shops at the company. So he had to convince them to do so. He also reached out to his colleagues from the dark matter collaboration in Europe, in the US, and in Canada. In Canada, he called up Nobel Prize winner Art MacDonald at Queen's University, who you can see here on the right, and asked him for help from the Canadian particle physics community. And within days, Art had assembled a Canadian team involving Canadian nuclear labs in Chalk River, Snow Lab in Sudbury, and TRIUMF, Canada's particle accelerator lab here in Vancouver. And he also secured the help of researchers from various partner universities of the MacDonald Institute for Astroparticle Physics. Everybody was just incredibly eager to help and pretty much dropped everything else just to jump on this project to help humanity in this crisis. You may ask, why physicists? And why do national labs for physics have anything to do with a ventilator and I could possibly be qualified to develop a medical device? Well, to answer this question, I show you just one example here of a detector system in these pictures that we recently built at TRIUMF for an experiment at CERN in Geneva, Switzerland. And this experiment will determine if the gravitational force for anti-hydrogen is the same as for hydrogen, so matter versus antimatter. But the point on this picture is really that you see a gas cylinder that is equipped with custom-made electronics, the red boards that you can see all along the detector and in the left-hand picture. It has gas handling controls, sensors, and so on. And this is just one example of the types of systems particle and nuclear physicists are designing and building as a matter of course for their research. These systems involve the same type of technology that is needed for the ventilator: gas handling systems, custom-made electronics controls and valve control and sensors, data taking, data display, and data analysis tools. In comparison to such complicated detectors, the concept of the MVM ventilator is actually quite simple. And it's shown here in its very initial version. It only involves an input valve, PV1 here, that controls the flow and pressure of oxygen to the patient. And there's a second valve in the exhalation branch of the breathing circuit that is closed during the inhalation flow, so air really is entering into the patient, and then is open during the exhalation so that air can escape. The valves are controlled by a microcontroller that reads the pressure from a pressure sensor near the patient mouth and opens and closes the valves just so to provide the right breathing rhythm and the right pressure, and monitors and controls the breathing of the patient. So the intelligence of this simple system is actually within this microcontroller and the associated electronics and software programming of this device. And that again is a lot of the expertise that the physicists have and brought to the table. The big difference of this system is that even though it's quite simple, it has a human being attached to it. And that is a game changer in designing such systems, because a medical device has to be much more safe than a physics device in terms of its performance, stability, and control. So the safety considerations are much more stringent, and that was a big learning curve for us. So in the early days, the team set up work at LMaster. You can see this in these pictures. And the work was guided by clinicians in hospitals in Italy, in the US, in Canada, and also mechanical ventilator experts that we arranged for consulting on this project. This really made sure that we were following best practice in developing a ventilator, and we're really building a device that the patients needed and that the clinicians could use. Within 1 week, we had a benchtop model that you can see here on this table together. That's obviously very cool. You would not put that to the bedside of a patient. The design efforts were obviously also guided by the medical device standards for ventilators that governments have put out there and agencies have put out there, and those were available from the UK, the US, and Canada. We also worked directly with manufacturers in Italy with LMaster, and in Canada with a company called Vexos and JMP Solutions. And this ensured that what we were designing was actually manufacturable in large quantities. And it was making sure that the parts could actually be secured and bought through their supply chain expertise. At TRIUMF, we immediately put a team together to aid the efforts. We had to quickly learn how a ventilator works. None of us knew anything about ventilators when we started. And from parts that we had in the lab, we basically MacGyvered a prototype together that you can see here on the left. It looks pretty crude and clunky, in particular in terms of the gas handling systems and so on. But you also see it already has this wet electronics board that we quickly designed and built with a microcontroller that allowed us to learn how such a ventilator system, a gas system, would be controlled, how the data would be read and displayed, and so on. So this effort enabled our team then to help the international team in the design and development effort, because we could actually play and learn on the fly how this worked and what had to be done. Only 3 weeks into the project, on Easter Sunday, one has to note in Italy, Easter Sunday, we worked basically right through. We had built the first 5 prototype units, pre-production units, as we would call them. And you see the plumbing inside is still rather big. You see the microcontroller in the box here. You see the displays on the boxes in the left. These were then distributed and shipped to Canada, to the US, to Spain, to Italy, so that the testing effort and the development effort could be spread over several places, and more people could get their hands on the same system, the same software, the same microcontroller, and aid the development. When we received the prototype at TRIUMF, we immediately set up a testing site. We were very fortunate that the BC Institute for Technology, allowed us to borrow one of their breathing simulator, which you see here all the way on the left, from its School of Health. This artificial lung can simulate the patient behavior and measure the ventilator performance. And it's really a critical gold standard for benchmarking performance of ventilators, and was essential for our testing programs. And we're very grateful for BCIT to make that available for a long time, actually. With input from the tests and the mechanical engineering support from Canadian nuclear labs in particular, design progressed and was made more compact. You see here a CAD drawing, so that one could actually assemble this in large quantities. And the aim is ultimately to assemble about 100 units a day. And so here is the final design, and look into the box, much more compact. The custom-made electronics is visible, and actually the valves were also custom designed by a Italian company, Camozzi, just for this purpose. And they jumped into action to modify some of their existing designs very quickly. So within a non-stop effort, working around the clock pretty much for 4 weeks, we were able to take this idea from a benchmark solution that you see all the way to the left on these pictures, through different prototype stages that you see on the table, to the picture on the right, which is the manufacturable device, the industrialized design of this MVM ventilator. 4 weeks. Now, what's in the box is slightly more complicated than what was originally envisioned. The main concept is still the same, with the breathing being controlled by 2 valves. You see this V1 valve on the left side, and at the patient breathing exhaling circuit, the other valve. But the system has now added various regulation and relief valves, more sensors for pressure, for flow of air, for oxygen concentration. And all of that was added to better control the operation of the ventilator and the breathing of the patient, and also for the safety of the patient. So we would know at any time exactly what was going on, and if something was to fail, it would fail in a safe mode for the patient. And that was part of the learning process and guiding process by the clinicians and the ventilator experts that we had on board. TRIUMF was probably one of the most crucial testing sites outside of Italy, and our teams of scientists, engineers, postdocs, and students put the MVM through an extensive testing program with hundreds of performance and failure tests. Because every functionality of the software had to be tested rigorously to make sure it complies and the system is safe. And on a daily basis, we reported issues and improvement suggestions back to the development team in Italy. And the software team then provided updated software on a daily basis, which then had to be taken through the full testing program again. For weeks on end, TRIUMF scientist Greg Heckman, who was leading our testing team together with engineer Nicolas Massacre. Greg is seen here in the bottom picture in a recent CBC Radio Canada piece on the MVM that you might be able to look up. And he would start his day basically with a phone call with Cristiano in Italy. Cristiano would summarize the progress that the team had made in Italy during the day, any new issues they encountered, and would work out a plan for the work at TRIUMF for the daily activities. And then Greg would end the day with another call at Cristiano at 10 p.m., 7 a.m. in Italy, to report back and help set the direction for the work in Italy for that day. And that went on for every single day for 6 weeks or so. A tremendous effort. Ultimately, this rigorous testing and development program ensured that the ventilator is fully compliant with medical device standards and completely safe for the patient. So what does it actually do? Well, here's a picture of the lungs, where you see the airways, the bronchial tubes, and the small alveoli air sacs that are transferring the oxygen into the bloodstreams at the end of the bronchial tubes. As physicists, that is a very complicated picture. So we simplify this and think of this more like we have the airways. They form a certain resistance to the air, and the alveoli can expand when they are when air is pumped into them. And so the lungs expands. It has a certain flexibility, or what's called compliance in this case. And that's really due to the about 400 million alveoli that you have in your lungs. Now, if you want to push a certain volume of air into the lungs, but the lungs are not very flexible, and that's the case in COVID patients, then it's very hard. You have to push very hard to get the air into the system. And then means you have to put very high pressure onto the lungs. And that in turn can actually damage the alveoli themselves, a condition that's called barotrauma. And that's something you have to avoid. The patient is already suffering from an inflammation of the lungs due to COVID. And doctors have actually described the situation as trying to push air into a brick when they were talking about ventilating a COVID patient. So for COVID patient, it is very important not to exceed a certain pressure in the lungs. And so the air is delivered in what is called a pressure-controlled ventilation mode. And that is what the MVM has been built to do. So on these pictures on the left, you basically see on the top the airway pressure. The ventilator ramps up the airway pressure during the inhalation phase, quickly keeps it at a maximum pressure that one can set. And then once the inhalation phase is over, the air is allowed to escape and the flows back out of the lungs. We also keep a certain base pressure that's above the ambient pressure, which is called PEEP, positive end expiratory pressure. And that is important so that the alveoli stay a little opened at the end. There's still some pressure in them. Because if in an inflamed lung, they would collapse, they actually fill with fluid and they may not open the next time around. They get basically stuck. And so then they cannot oxygenate the patient, and that's obviously bad. On the right, you can see how that's realized on the display of the MVM, the pressure profile of several breaths, the volume that's measured, and the flow that's measured. And you see there's also all kinds of other measurements that are taken on weight and various other information that's important for the respiratory therapist. So let me show you quickly the MVM in action, and I hope you can see and even hear it. This is how it's been realized. You see the little test lung at the bottom right expanding in every breath, and the display has been tested with respiratory therapists for usability. It's easy to find your way around and change parameters and change how the patient is ventilated, and there's all kinds of alarm settings as well to ensure that the patient is safe and the performance can be monitored. So this massive team effort of our international collaboration, there's maybe between 50 and 100 people involved at any given time, has enabled the development of this now commercially available ventilator that you can see here in its full realization in the picture. in a speed of less than 5 months to get the product ready. And then it took another month or two to get Health Canada approval at the end of September. The government of Canada had already indicated in its efforts to secure more ventilators for the country in April that they would purchase 40,000 additional ventilators, 10,000 of the MVM if we could get Health Canada approval, which we just achieved. So the government signed in May a contract, and now we can start production of about 800 units a day to deliver to the government. And if you go to the Vexos website, you can actually now order a quote for this ventilator. It's produced in Markham, Ontario, and it costs only a fraction of an ICU ventilator, which typically run on the order of 20 to 50,000 US dollars. This comes in at about 6, so it's not super cheap, but it's much cheaper than the high-end ventilators. And at the same time, it does provide the care needed by COVID patients in a safe and reliable way. It also makes this price range makes the MVM a good candidate and a good option for developing countries, which cannot afford to buy large amounts of the high-end ventilators, but may be able to purchase more of these. So let me close by saying that this project really has only been possible because of an incredible effort and the dedication of a large international collaboration. And I show you here only the Canadian partners. The team was spread over 9 time zones. Typically, that's considered a burden for any kind of work arrangement. However, in this case, it allowed us for rapid development of this product around the clock. And finally, let me conclude with the observation that the MVM development is just one demonstration of how the physics community, and in particular major physics laboratories like Canadian Nuclear Labs, Snow Lab, and TRIUMF, are able to bring their expertise together and help in a crisis and help the government and the society to address that crisis. And with that, let me thank you for your attention. I'll be happy to answer any questions, non-medical questions, because I'm not an expert. Please stay safe, and I hope you never need to actually use one of these.
So now I would like to invite people in the audience to submit questions via the chat box. Okay, so while we're waiting for questions from the audience, let me ask a question. This ventilator is much cheaper than the commercial ones. What compromises had to be made in order to achieve this low price? And does this satisfy all the functions of commercial ventilators?
Well, it doesn't do everything a commercial ventilator does. For example, I mean, I mentioned that we are only concentrating on this pressure-controlled ventilation mode. There are many different modes a full-blown ventilator could do. You can control by pressure. You could actually use it on infants, which this system is not designed for. Some of these modern ventilators are very smart in their response to issues and try to figure out how to react. In our case, we typically go into a safe mode and require the therapist to interact and do something and fix things. So it is much simpler in that respect.
Okay, we have one question from the audience. What kind of microcontroller was used?
So there's, in reality, it's actually 3 different microcontrollers in, and one of them is, which is the main controller for the valves, is a kind of Arduino-based microcontroller. And the display, which is controlled by a Raspberry Pi, and the associated screen has been used. And the third one is actually a very special supervisor microcontroller that makes sure everything is running and just monitors the others for activity.
So another question was, this ventilator seems to be only usable in a developed hospital setting where they have oxygen at the correct pressure and so on. Is that right?
That is correct. We are, part of our team has continued working on developing a system which may produce basically concentrated oxygenated air at the right pressure directly, which could be added sort of as a system. But that's an ongoing development.
Okay, another question is, what role is there for physics researcher at this point in the pandemic going forward?
That's an interesting question. There is, I mean, always new ideas are welcome. I mean, this was obviously developed with in a rush to really try to get it to market even quicker than we originally had hoped to even be quicker than this. There are efforts for even cheaper ventilators, which might help in absolute crisis modes and only come in around $1,000. And those efforts, I think there's many of those still active, and some of them involve physicists, certainly lots of engineers involved. That's sort of what comes to mind right now. And maybe the effort that we hear about from Dean Karlen in terms of helping on the computational side. We are also using our computational resources at TRIUMF to help computational activities on protein folding and so on to really understand COVID better. And though we have that for our large detectors activities at CERN, we've made some of those resources available for these calculation efforts.
Okay, one final question. How do the safety features work?
Well, the safety features, there are numerous safety features. Basically, you always, whenever something goes really wrong, the system has to end up in a safe state, which means the patient can breathe unobstructively, and obviously an alarm has to be raised so that somebody pays attention and intervenes. So we monitor, we have some hardware safeties like pressure relief valves, so pressure can never go over certain boundaries, and make sure that that is always the case. And then others are safeties where you just measure pressure and set alarms, thresholds. And there is this supervisor module that basically looks if the microcontrollers hang up, for example, for some reason, and if they were to do so, the supervisor puts the system into a safe state and makes sure that the patient doesn't get too much pressure and the breathing circuit is unobstructed.
Okay, I think that's it for the questions from the audience. So let's thank Reiner again for this very inspiring talk. Thank you, Reiner.
Thank you. It was great to be here.
Okay, so now for our second talk this morning by Professor Dean Karlen at the Physics Department in the University of Victoria. He will explain how his data science expertise has been employed to model the spread of COVID-19 and inform government policy. So again, this will be followed by a question period. I invite you to submit questions on the chat. Okay, Dean?
Well, thank you, Stan, for that nice introduction. Yes, I'll talk about modeling COVID from a physicist's perspective. And just to give the background, as Stan said, I'm a professor in particle physics at the University of Victoria, but I'm holding a joint appointment with TRIUMF. And my experience is primarily in building experiments, something like Reiner had shown, and analyzing data in particle physics. But in March, I started to learn about how the modeling of the spread of COVID-19 was done, and developed a model based more on a physicist's perspective, which is, I think, different than the perspective of many modelers in the epidemiology side. So from a physicist's perspective, we like to incorporate fundamental workings of a system into models, keep these models as simple as possible, and realizing that no model that we would write or develop would be perfect, but focus on its main purpose to interpret the data. So that was the purpose of the model that I developed. You're welcome to visit this website to see results from that model, pypm.ca. It seems to be working fairly well, and it does allow us to learn things from data, and that's what I'll be showing and sharing with you today. So I've also been engaged with other modelers since April, engaged with the British Columbia CDC modeling discussion group. A few times a week we discuss the challenges in modeling, and also since July I've been a member of the US CDC COVID modeling and forecasting group. And certainly by looking at US data, it's a very there is a lot of data from the United States, certainly a lot of cases, and that data makes it very useful to challenge our models. So that's the reason that I'm also looking at US data. But just as a quick look, the CDC forecasting group is quite large, a large number of universities engaged. And just as a most recent comparison of the performance of forecasting, this was a list compiled by an independent person that was looking at how accurate forecasts were, 1 to 6 weeks prior to a particular week of data. And I'm happy to see myself in the higher group of, more accurate forecasts. Probably one of the forecasts you hear a lot about certainly wasn't performing so well for that period. It's down here, but you see a lot of effort and coordinated effort there by the US CDC. And a few of us are also forecasting hospitalization growth in the US. Just 8 of these groups are doing that to forecast special for every state where there may be special needs for attention to growth in hospital utilization. So in this presentation, I'd like to give a feel for you about how these models work internally. I won't be talking too much about the math, but I will talk about the general features of these models. So for every model has what's called an infection cycle. So how new people are infected. So we need a susceptible population and a contagious population, and combined, those produce newly infected people. The number of newly infected people, I won't have many equations, but showing this one here, is proportional to the number of contagious people, essentially. There's some transmission rate, called the Greek letter alpha here, and multiplying that by the size of the contagious population effectively tells us how many newly infected people there are in one day. So it's called a cycle because we have the infected people producing newly contagious people. And so it has the problem of a positive feedback that produces more and more contagious people. So effectively, if all of the newly infected people immediately become contagious, the number of newly contagious people in one day depends on how many contagious people there are with that proportionality constant. So this is what happens. So if on day 0 we have C0 contagious people, and then a new set of contagious people are produced, then on day 1 we have 1 plus alpha times that original number of contagious people. And now if we look further into the future, we have this relation, which means that we have exponential growth. This is the same formulas that tell us how our investments grow if we have a constant interest rate. So that exponential growth is what we have to be very concerned about with any pandemic like this. When we show this growth is very shocking, especially if you look for more and more days. If we make show this behavior in a different way so that the vertical axis is called a log axis, then that same growth appears as a straight line. So some of the pictures I'm going to be showing will show that straight line. Now, we use these graphs like these to show what's happening and to tell the story of the past history and also to look into the future. So you'll be seeing many of these kinds of curves, and I'll also be overlaying the data that we have been seeing on these sorts of curves. Now, fortunately, we don't just have exponential growth from the newly infected, but we also have some depletion of that contagious population. And that is because people stop becoming contagious because they either recover or they have some symptoms that cause them to be isolated from the population. So because we also have that depletion, we will either have exponential growth or exponential decline. So it's still an exponential function. That is, we still have this I in the exponent. But this amount of change per day could be positive or negative, depending on whether or not we're growing in the number of contagious people each day or declining. So just to give a feel for the period after April, after shutdown of various social measures came into play, that transmission rate, the average number of people infected by one person per day, is generally in this range from 0.1 to 0.25. And that produces a growth rate somewhere between -5% a day and +5% a day. So we'll see some of that for some jurisdictions. But essentially reducing the social contacts, which we did after March 18 in British Columbia, that reduces that transmission rate, the number of contacts you have. And therefore it reduces this exponential growth factor. So we'll be using the data itself, the case data, to tell us what these transmission rates were and when they change. We can see dramatic changes, for example, when the government imposed the social shutdown, just like in British Columbia on March 18. Prior to March 18, the epidemic was growing at a rate of 20% a day, approximately. So you can imagine how well your investments would do if you had a 20% return per day. Of course, in the case of an epidemic, this is very frightening. So after March 18, those lockdown measures were enforced by the government, and we changed our social behavior, and as a result, the growth changed from plus 20% per day to -5% per day. So what I'm showing here is the data itself in the number of cases, positive cases, as they accumulate over time, starting from March 1 to June 1 here at the end. And the green curve is the model that only uses the fact that there were two transmission phases, one before March 18 and one after. And on the right, I'm showing the same data, but in that special way, I call it a log plot, where we see that exponential growth is a straight line up, and now we see the exponential decline, a straight line down. But we also see the hospitalization and the ICU, ventilators, and deaths as well, all of that data. And these curves are the model prediction that are based simply on the case data itself, and also inputting what fraction of people go to hospital or ICU or die. So you can see that this model does pretty well predict the general behavior of the demands for hospitalization and also of the number of deaths that would result. So you can see that it's not perfectly modeling it, but that's because the behavior and the probabilities of going to hospital it is a probabilistic situation. So you will have variation around this model prediction. And on the right, sorry, on the left is the data itself, and on the right is just a typical simulation from the model of data where we see the same sort of variation. So we can expect that kind of variation, and we can reproduce that variation in the model. So one thing we can look at with a model like this is to say, well, what would have happened had the government waited, say 1 or 2 extra weeks to take action rather than acting on March 18? Had they acted a week later or 2 weeks later? You can see that this is the model here, the green model now isn't turning over for another 2 weeks. It's extending well beyond when we actually turned over. So had the government waited 2 weeks, there would have been 10 times more deaths in British Columbia. The numbers in the ICU would have exceeded capacity as well. So of course, governments having their own models and knowing this behavior, it was very important to make these lockdowns early while even the cases are low, because they understood the consequences, because they had models like these. So since May, we've seen 2 other phases in British Columbia. After that decline of 5% a day, we've had since June a growth of about 2.5% per day. And then in the last months or so, it's been roughly constant. And I was going to mention here that you can see that initially the hospitalization and ICU usage were more or less following the prediction from the model. But during this growth phase in the summer, that no longer was tracking. And this was due to the fact that primarily younger people were responsible for this growth in cases, and their needs for hospitalization were lower. So it was no longer a suitable model to model this situation. Here is a demonstration of how much growth there was in the younger population during that June, July, August period as compared to an older population. You can see up to June is similar numbers of people with positive cases here, but then if we look to now, it was primarily younger populations that were growing. And so our models up until now were homogeneous, treating everyone as just equal. That's not sufficient to model these circumstances now. So I've incorporated into the model the ability to have a heterogeneous population. That is, a population having different age groups in that model. And so we have just illustrated here age group A and age group B. And now the contagious people are not just within their own age group. There's other age groups that are contributing. And so having this mixed combination of different populations introduces new features or new behaviors that hopefully will properly model the situation for the cases where different age groups are behaving differently. They certainly do have different hospitalization and death probabilities. So I looked to California data to be able to check and to test this kind of a model that breaks it into ages. And we saw in California, after their lockdown, they actually didn't decline. They were continuing to rise, and then went into a very fast rise phase after Memorial Day. And then somewhere in July, early July, a decline. Now, it's not exactly clear what caused this behavior change. perhaps something to do with the mask order that was imposed. But this is a very useful data set because there are so many cases involved, and we have that data for different age groups. So you can see the younger age group, the middle age group, and the older age group all had that feature of growth and then decline, phase 2 and phase 3, I call it. Actually, the growth rates, these are in percent, are all quite similar. But you can see the deaths and the hospitalizations are much more significant in the older age groups. So what I've done with this model is to model this entire situation with mixing between these populations. And this graph is way too complicated, so I won't explain it unless there's a question about it. But we have to assume something about the mixing, how much mixing there is in between populations. And that's an uncertain situation. But effectively what this picture is showing is on the horizontal axis is the social contacts for the younger population. So to the right is, many more contacts, to the left is less. And so we went from this phase 1 of low growth to really quite much faster growth. That corresponds to the younger population having much more social contacts. Now, if we put in a reasonable amount of mixing as shown here, that transition from that phase 1 to phase 2 did not really change the older population. They didn't change their social contacts much, or the oldest population, they didn't change hardly at all. And so this growth that we saw in all of the age groups is primarily due to the young, if we have this modest amount of mixing. And that has huge consequences. If we use that mixing and now we just look back and say, well, suppose we just asked the young group not to engage in so much social mixing, and suppose they had the same amount of social contacts as the middle age group, how would that change the situation for everyone? So that's what's shown in the solid line here is the number of contagious people as a function of time over those 6 months or 8 months, and for the different age groups. In the dashed line is if just the younger people had behaved more or less like the middle age group. You can see the biggest effect in terms of the number of contagious people is in the younger population. But if we look at the more serious consequences, the number of deaths, the number of hospitalizations, particularly the number of deaths, that behavior did cause an increase in the number of deaths in the younger group, but it caused a substantial, at least according to this particular modeling, a substantial growth in the number of deaths in the older population. And this was primarily due to the phase 2 growth in the younger population. So it had very serious consequences for that, for this particular, at least as interpreting this with this particular model with that much mixing. So I think my time is coming to an end. I was going to also mention that we can also use this kind of model to consider the vaccination that will be coming into the future, and whether or not there should be an age-based vaccination strategy. So we can use that same model and apply, different vaccine effectivenesses. Perhaps the vaccine might be less effective for older people. We need to know what kind of vaccine hesitancy there is. If all the age groups were isolated from one another, it would seem clear that you would vaccinate the most susceptible and those with the most severe consequences. That is, vaccinate the oldest first. But there are situations where that might not be the best strategy. And just to finish, I thought I'll skip right ahead here and show the situation if, here it is, if the vaccination was much more effective for younger people. And remember, it's the younger people that can be driving a lot of the growth in the cases. So if we consider this model and we vaccinate the population, we can look at a situation, what will happen and this is again the California population. So the vaccination starts on day 150, and the dashed lines are without vaccination and the number of deaths, and you can see it grows significantly. And then with the vaccination, the number of deaths is shown here. But if I change it to a vaccination schedule where the oldest get vaccinated first, it turns out that under this model, the total number of deaths do not change significantly. And of course, what's happening is that if everyone gets vaccinated at the same time, that's the course histories, and then I'll change it to the case where the oldest getting vaccinated first. Yes, there's a decrease in the number of the older population. You can see it go down. But you can see in the younger populations, the deaths go up. So just to summarize, the work to understand and control the spread of COVID-19 can benefit from physicist perspectives and approaches, the kind of methodology that I was mentioning here. We do bring along different skills or mindsets on how to treat data, and certainly we have a lot of experience in data analysis. And I should mention, of course, that the study that I was showing here about mixing of different ages and the implications for vaccination, this is all very preliminary work. It was just shown as an indication of the kinds of questions that we can study and talk about with these models. And so with that, I'll give it back to you, Stan.
Okay, thank you, Dean. So I invite people in the audience to submit questions via the chat box. There are already a couple. One question is, you said since June, it's been constant. Do you mean the infection rate?
Well, so I assume this question refers to the British Columbia situation. If we look at the British Columbia data that I was presenting here, this was the number of positive cases for days since March 1, and way over here on the right is essentially today or yesterday. You can see there's large variation from day to day in the case numbers. This is just primarily due to reporting. Sometimes there's a backlog and then they report back and forth. The model that I'm showing here is more or less a representation of how many cases we would expect. On the right is the number of contagious people. You can see it's roughly constant because the number of cases per day is constant. Oh, the stars here, by the way, are the 1 week averages. So you can see it's a less scatter in those points, and it follows the model pretty well. So yes, the number of new contagious people is more or less equal to the number of depleted contagious. So we have more or less a constant population of contagious people over the last month or so within the province of BC.
Okay, so another question is, from the data, it seems that we should vaccinate the young people first. And can you make that acceptable from a social perspective?
Yes, I mean, one has to take into account a lot of factors in defining the vaccination strategy. Now, I'm not saying that there is a case to be made yet to say that the young should be vaccinated first. We need to know how effective the vaccine will be to different age groups, and that will be part of these phase 3 trials of vaccination. So we don't have that data yet. The other thing that is really important and is not, I did not show or talk about, is the fraction of an age population that will be willing to get vaccinated. That's going to play a big role. And so all of these things need to be understood and brought into the modeling to decide if indeed there should be an age prioritization, or should all ages be vaccinated more or less at the same time.
In your models, you showed that the efficiency of vaccination is much higher in younger people than older people. Is that known to be true?
Yeah, so when you're doing these models for something in the future, you have to just consider different possibilities. So this was just one consideration. I was considering, well, should it be the case? And some of our people in BC CDC think that this might be a possibility, but it's not certain. This is something to consider. If we find out this is the case, then that will influence the strategy for vaccination. So no, I'm not stating that this is the case. It could be the case. But when we're doing these modeling, we want to consider different possibilities. So I've also considered the case where it's equally effective on all populations. And in that circumstance, I guess I can just go back and forth here. So this is everyone getting vaccinated at the same time, then the oldest getting vaccinated first. Again, you see a strong decrease in the number of people vaccinated or in the older group, whereas there's a slight increase in the deaths for the younger group when everyone has the same effectiveness, or the effectiveness is 80% across ages. So it does depend on these assumptions, and hopefully we'll have that data in the coming months.
Okay, so another question is, what assumptions are involved in incorporating behavior into this type of model?
Yes, it's a great question. So there are modelers who try to model social behavior, and as such also try to predict what decrease there will be in the transmission of the virus should a certain activity be stopped. Now, I don't, in my model as a physicist, I realize that I will not be able to predict that. I will not be able to model that kind of detailed social interactions. It's too hard for a physicist to do that. So in this model, I am using data to tell us how social interaction has changed by simply looking at how fast the epidemic is growing, and then how fast it is declining. And so it's just the case data itself that tells us that factor alpha here, that transmission rate. So I don't need to try to model social behavior. I just use the case data to tell us the important features of case data, the most important feature of how fast the epidemic is growing or declining at different phases as we see. So these transitions aren't predicted, those days aren't predicted, and the rates aren't predicted. They're measured from the data.
Okay, now could your model take into account the rate of vaccination in the population?
Exactly, yes. So for the vaccination, you must include a vaccination rate. And I was assuming, just for the case of California, 200,000 vaccinations a day, that will take 150 days to vaccinate everyone. So for example, this one mode where we're in this blue line is showing how many people are getting vaccinated. So everyone's getting vaccinated at the same time, and then we see the consequences of that. Or you could vaccinate the oldest first, so you see this group everyone gets vaccinated, and then this group starts getting vaccinated, and this group starts getting vaccinated. So indeed, you do have to, you don't just assume you can vaccinate the entire population in one day to calculate the consequences. You have to put in a vaccination schedule.
Okay, and one final question. Do you have to model the cost or side effects of vaccination on different age groups?
Yes, that's another interesting question, which of course would be part of the overall social or public policy decision process, to consider all of the various consequences and costs and possible other factors. But in terms of this model, I'm simply looking at hospitalization, deaths, and that connection. So don't have other factors included.
Okay, so I think our time is up. So let's just thank both speakers for both of their presentations today. And I thank everybody in the audience for your participation. So hope to see you all again next month at our next Saturday morning lecture.